Delaware Tech, Chemistry 100, Chemistry 110, Unit 4 continued, ionic versus molecular or covalent compound properties. So we've talked about ionic compounds and molecular compounds, but let's talk about the properties. We've mentioned a number of these already, but there are a lot of different properties that vary considerably when you're comparing ionic compounds versus molecular compounds. Remember, molecular compounds are also called covalent compounds because they are composed of covalent bonds holding the atoms together. So the types of elements you find in ionic compounds are almost always metals and nonmetals together. Occasionally you'll find some polyatomic ions that happen to be positively charged that can replace the metal cations, but in general the vast majority will have a metal and at least one nonmetal present. Whereas molecular compounds tend to be only composed of nonmetals. In other words, the elements on the right side of the periodic table. This compares to the ionic compounds where you typically find something from the left side of the periodic table in bonds, in ionic bonds, with something on the right side of the periodic table. The types of bonds are very different. We've already talked about these. In ionic compounds, they are distinguished by having ionic bonds. So you have attractions between the positively charged cations and the negatively charged anions, and these attractions are kind of generalized attractions so that one positively charged ion will attract many negatively charged ions around it and vice versa. So you end up with these very large complex lattice structures, these crystal structures as shown in the bottom here. Whereas covalent compounds, also known as molecular compounds, are composed of covalent bonds. So the atoms are sharing electrons, and they tend to be relatively small in comparison. They are very distinct molecules that are separate from each other. Whereas when you're looking at ionic compounds, there is no separate molecule. So we call the separate piece of an ionic compound formula unit, but there really is no separate piece. What that just represents the simplest formula version of the entire crystal. So if it's a 1-to-1, we would have a formula with one atom of the first and one atom of the second in the formula, as opposed to a 1-to-2. Whereas molecules have a very distinct individual structure and formula. Now the polarity, meaning how much of a difference in positive and negative charges in the molecule or compound, in the case of the ionic formula unit, if there's a large difference in electronegativity between the different components, we see polarity. And most ionic compounds are very polar, and the reason for that is they're composed of cations, which are usually from very electropositive elements, in ionic bonds with anions, which are usually derived from very electronegative elements. So you have this positive charge on one side and this negative charge on the other side. Whereas molecular compounds are these discrete structures, and there might be some partial positive charge in some of them and a partial negative charge in some of them, but there are no formal charges, so they tend to be much, much less polar. And because they are much less polar, they don't usually dissolve in water very well. They tend to be fairly insoluble. There are lots and lots of exceptions. Whereas ionic compounds, most of them are quite soluble in water. They're composed of ions, and when put in water, the ions break apart. This lattice breaks apart into individual ions that end up being surrounded by polar water molecules. So water is one of those examples of a very polar molecular compound. So there aren't a lot of them, but there are some that are extremely important, like water. And water is very polar, so anything polar, like ionic compounds, is soluble in polar, whereas nonpolars tend to be soluble in nonpolar solvents and don't tend to be soluble in polar solvents. So likes, and things that are different don't tend to be soluble in each other. So polar prefers polar, nonpolar prefers nonpolar. Melting point and boiling point. Ionic compounds tend to have very high melting points and very high boiling points. Well, how do you know that? Well, just about every ionic compound there is a crystalline solid. If it's solid, that means that room temperature is not warm enough to melt it and certainly not warm enough to boil it. So it's a solid. And the reason why is, look at the structure of ionic compounds in the bottom here. They are lattices. If you break apart a little bit of it, it will still be held together by the attraction of all the other atoms surrounding it. So it's very hard to break apart all of those bonds, or a large portion of those bonds to melt it, and then all of those bonds to actually vaporize it to turn into gas. Whereas molecular compounds, being these discrete individual molecules, they have interactions that hold them together, and there are some molecular compounds that are solids, but a lot of them are liquids and a lot of them are gases. So it's much easier to break them apart, and therefore it's much easier to melt them and much easier to boil them. So they tend to have low melting points and low boiling points. And as a result, the ionic compounds are almost all solids, whereas you'll find solids, liquids, or gases depending on which molecular compound you're looking at. Carbon dioxide is a gas. Water is a liquid. Large hydrocarbons can be solids. So it all depends on what compound we're talking about. So how do you determine which is ionic and which is covalent? Well, there's a mathematical way, but we're going to do that much later when we're talking about the bonds between atoms. But right now, we're just going to use the quick and dirty way, which is to ask, does it have a metal? If it doesn't have a metal, it's probably covalent or molecular. And if it does have a metal, it's probably ionic in nature, because if it has a metal, that's the electropositive portion, and it'll also have a non-metal, that's the electronegative portion. So that would make it ionic. One side would be positively charged, one side would be negative. Remember, the atoms on the left side of the periodic table, left being defined as all those gray metals that are listed here in this periodic table, they tend to want to form cations, positive charges, and all the ones on the right tend to want to form negative charges. But if you only compose your molecule of things on the right, they don't form charges at all, they share electrons, and then they become covalent. So ionic will have a metal, covalent will not have a metal, usually. So let's look at the first compound, P2O5. Phosphorus is over there on the right in the nonmetals, but so is oxygen. And you're really only looking at the first atom, because the way these structures are written, you always write the more electropositive atom first, or the one that will become a cation first, and therefore you just look at the first one and ask, is it a metal? If it is, it's probably ionic. If it's not a metal, then probably none of them are metals, and then it's covalent or molecular. So phosphorus is not a metal, so that would be covalent or molecular. Magnesium, look in the second column, magnesium is a metal, ionic. Sulfur, not a metal. Nitrogen and oxygen, both nonmetals. Sodium, Na, is a metal. It's one of the best metals. It's over there on the far left. Iron, this is iron oxide. It's composed of iron and oxygen. Iron is a metal. Aluminum, chloride. Aluminum is a metal. Chlorine, pentafluoride. And we'll learn how to name these later. But chlorine pentafluoride, chlorine and fluorine are both halogens. They're both non-metals, covalent. Tetraphosphorus decaselenide, or P4Se10. It's composed of phosphorus and selenium, both nonmetals, covalent. Silicon and two seleniums. Well, the reason why I was hesitant to name it is because there are a couple different ways to name this, and that is because silicon, you'll notice, is one of the middle elements. It's a metalloid or a semi-metal, and therefore, technically, it could be considered an ionic compound or a covalent compound. So we'll just call it both right now, and either answer would have been fine. Cobalt, CO2Te3. This is cobalt-3 telluride, and this would be containing cobalt. And cobalt, if you look right in the middle of the periodic table, on the top row of the transition metals, you see cobalt is a metal. So that's ionic. And I'll let you do the rest of these. Look at the first atom, chromium, iodine, calcium, Cu is copper, C is carbon, P is phosphorus, C again, Hg is mercury, Ni is nickel, Ge, germanium, and look on the periodic table where Ge is, germanium, and it will give you a hint as to what kind of compound it could be. And Au is gold. Towards the right side of the transition metals in the third row of the transition metals. And go ahead and test yourself. I'll pause here, and then I'll reveal the answers. Okay, here are the answers. And you can see how well you did. Now, let's talk briefly about the types of solids out there. And you can break up solids into different kinds of categories. One way to look at them is, are they amorphous, literally without shape, or crystalline, which we've already started talking about crystals that you always find with ionic compounds. They end up forming very specific lattice patterns. But amorphous refers to no defined shape. The molecules are not in any specific pattern. The atoms and the molecules are not in any particular position. There are lots of examples of amorphous solids. Silica glass, which is the glass you see in windows. Obsidian glass, this is from molten lava that's cooled very quickly, so the atoms have not had time to arrange themselves in a nice lattice, so you end up with this black glass. Cotton candy, gels, thin metal oxide films. So when you have some pure metal on the outside, you start getting it oxidizing, what we would call rust if we were talking about iron. These films tend to be amorphous, not having a real structure. Many metal alloys, mixtures of metals, tend to be amorphous. Now this is compared to crystalline. Crystalline is where you see a regular pattern of the atoms or molecules in the structure. And we have crystalline solids. Most ionic compounds are crystalline solids. Many pure metals are crystalline solids. The metal atoms, they're atoms, not ions, the metal atoms actually arrange in very specific patterns. We also have what are called network molecular solids. These are solids composed of covalent bonds, but they look like crystal structures. Diamond and graphite are two examples of that. You also find crystalline structures among molecular compounds that have just been frozen, and they end up forming crystal structures when they freeze into the solids. And ice and dry ice, which is solids, carbon dioxide, are two examples of that type. So most ionic compounds, most ionic minerals like ruby, quartz, sapphires, etc., as well as a lot of metals, as well as these frozen solids like ice and dry ice, and some of these covalent large network molecules like diamond and graphite. So if we look at a comparison, we have these different, there's another way to distinguish solids, and in this case, all of these can be crystalline solids. Molecular compounds can also be amorphous as well, and so can some ionics if they're heated up and then cooled down very fast, and they don't have time to form crystals. But ionic compounds, remember, are formed with ions, cations and anions that attract each other. They're in a crystalline lattice. They have high melting point and boiling point because they're hard to melt. They're hard to boil. So they're solids. And there are lots of examples shown here. Sodium chloride, iron 3 nitrate, ammonium sulfate. So there's an example of an ionic compound that doesn't have a metal because it has ammonium ion in it, which is positively charged. We'll learn about that in another module here. Molecular compounds are things like CO2 and water, things that have covalent bonds in them. All proteins like insulin are. And you can find examples that are solids, gases, and liquids. It all depends on which one we're talking about. They tend to have lower melting and boiling points. Shown in this picture here is water as crystalline water, which we also call ice. Network solids, as I mentioned, are large molecular compounds that have repeating structures. So they're like a lattice, but they're not made of ions. They're made of atoms attached with covalent bonds. Diamond, graphite, crystalline rubber, crystalline plastics are like that. Whether the rubber is crystalline or not, or plastic is crystalline or not, they are network compounds. But when they form these lattice structures, then we call it crystalline. Metallic metallic bonds. So these are just pure metals. Or occasionally metals with other metals. And metals as you know, conduct electricity. And the reason why is when metals are together with each other, they donate an electron, one or two electrons of their outer electrons that kind of form a sea of electrons surrounding the chunk of metal, and they can freely flow, and this is why these things allow electricity to flow through them. It's not that they form true cations and the electrons are free, but the electrons form this sea of electron density around it, which is one giant bond holding it together. So metallic bonds are actually different from ionic bonds and molecular bonds. We're not going to cover those in Chem 110, and we're not really, in Chem 100. We're not going to cover network compounds in Chem 100 either, but I wanted to go over these to cover all the types. And with this, we'll stop here for the next module.